Assalamualaikum warahmatullah. This is first part of tutorials for chapter 6. Let's try this problem. A steam power plant receives heat from a furnace at rate of 280 gigajoule per hour. Heat losses to the surrounding air from the steam as it passes through the pipes and other components are estimated to be around 8 gigajoule per hour. Okay, so that I underline the key information there. If the waste heat is transferred to the cooling water at this rate of 145 gigajoule per hour, determine net power output and the thermal efficiency of this power plant. Okay, so if we draw the diagram to describe this, okay, you have a source, okay, in the form of furnace there in the problem. Okay, and then the heat is being supplied to the heat engine. Okay, let's say that we have heat engine here. Okay, and the amount of heat supplied is given there, and this is QH dot 280 gigajoule per hour. And then we know that there is heat loss to the surrounding. So this is not going to the sink actually. Okay, let's keep that for a while. If the waste heat is transferred to the cooling water, okay, that will be going to the sink. So if you have a sink here, okay, which is a cooling water there, okay, and you are given that amount of QL is equals to 145 gigajoule per hour. Okay, and of course this is heat engine. We expect we're gonna have this work net out from the system. Okay, going back to this heat loss. Actually, heat loss is from the heat engine system. So we can say that there is a Q dot loss there. Okay, just to give some description from the heat engine. Okay, so basically that would describe the situation that we have in this problem. So the first part is to find the net power output. If you refer to this system, okay, you can see that the total heat rejected, okay, total heat rejected from the system, we can see that there are two heat rejected. One is due to the loss and the other one to the sink. So let's call this Q out. Okay, rejected from the system, which is nothing but Q loss, Q dot loss plus Q dot to the sink, to the lower temperature reservoir. And what we have here is nothing but Q loss is 8 gigajoule per hour plus 145 gigajoule per hour. So you have a total of 153 gigajoule per hour. That is the Q out. And from there, then I think we can put the energy balance relation. Okay. And we can get the net work out. In this case, you can specify out just to emphasize, but we know the conventional is a network. And in this case, heat engine is going out. Going out, and we have also going out due to the loss or Q out. So it is nothing but QH dot minus all the heat out from the system. So Q out. And we know that this is nothing but QH is given 280 gigajoule per hour minus Q out already calculated above 153 gigajoule per hour. That would be 127 gigajoule per hour. Okay. And if you want to convert this, of course, you can multiply or convert to watt. Then we have 1 hour equals to 3,600 seconds. So you can cancel the hour, and this would end up to be 35.3 megawatt. Okay, that would be the first part A. Now we go to part B, thermal efficiency. Now we know work net out. We know that for heat engine, the efficiency is nothing but work net out in this case, of course, okay, divided by how much heat is being supplied to the system, which is QH dot. Okay, so 127 divided by since you are using, it doesn't matter which unit, but you need to be consistent, gigajoule per hour divided by the Q dot is 280 gigajoule per hour. So we have the same unit there. And it turns out to be 0.454. And this is nothing but 45.4%. Okay, so that will be the answer for the second part. Okay, that is the first problem. Let's go to the second problem. Okay. An air conditioner removes heat steadily from a house at a rate of 750 kilojoule per minute while drawing electric power at the rate of 6 kilowatt. So we are removing heat from a house at this rate, 750 kilojoule per minute, and power requires, okay, or work requires that, well, rate of work requires is 6 kilowatt. Okay, determine the coefficient of performance of the air conditioner and the rate of heat transfer to the outside air. Okay, actually I should go to the next. Yeah, this one is the drawing board basically. Okay, if we are to draw the diagram to describe the condition, basically you have your house, okay, in the bottom because you want to extract heat from the coal, okay, right? And you want to transfer the heat, in this case, the heat from QL, okay, at the rate of 750 kilojoule per minute. Okay, that should go through the air condition, okay, aircon system. Okay, and we want to throw out that to the hot surrounding, which is your outdoor. And of course, that requires work net, and in this case, work net into the system. Okay. We do not know yet this, but we can specify in our so you have QL to be taken out from the house. So the air condition is taking out that heat and then throw out to the outdoor, and the work requires to do that is given as W dot net. Okay, and you are given actually the value, which is 6 kilowatt. 6 kilowatt is kilojoule per second. Okay. All right. Note that we have two different denominator unit there. Okay. So let's try this. So the first part, coefficient of performance. Okay. As we know, for a refrigerator, okay, it is the intended, which is we want to remove heat from the room. Okay, the Q dot L divided by the amount of work required to do the job. Okay, which is work dot in. And we have all the values basically. Q dot L is 750 kilojoule per minute. And let's be consistent in terms of the unit. So 1 minute is nothing but 60 seconds. And we want to convert to kilowatt. We know that 1 kilowatt is nothing but 1 kilojoule per second. And then network in is nothing but 6 kilojoule per second. All right, or kilowatt, doesn't really matter. Yeah, I don't think that we need that part. Hold on. Let me just erase. We can erase this. Okay, so we will end up with kilojoule per second. Okay, that is sufficient. And if you do this calculation, turns out to be 2.08. Okay, that is the coefficient of performance for refrigeration system. B, the rate of heat transfer to the outside air. Then again, you can use the energy balance relation. You can see that 2 is going into the system, 1 is going out. So the energy balance, you can say that QH dot is nothing but QL dot plus W net in dot. Okay, and we have, we know all of them. So basically 750 kilojoule per minute. Okay. Since the answer is in minutes, so we'll keep that. Plus work net is 6 kilojoule per second. Let's convert that. 60 seconds is equals to 1 minute. So we have kilojoule per minute there as well. Okay. All right. So if you do this, 360 plus 750, so you will end up with 1110 kilojoule per minute. Okay, so that will be the answer for part B. Okay, let's try one more problem before we end this part. Okay, 652, heat pump used. Okay, just now we were doing for refrigerator. Now let's look for heat pump. A heat pump used to heat a house runs about 1/3 of the time. Okay, there is several keywords there. Heat pump, and then it run only 1/3 of the time, meaning that out of the whole duration, only 1/3 is when the heat pump is running. So the rest, the heat pump is turned off. Okay, the house is losing heat at the rate of 22,000 kilojoule per hour, and you are given the COP of the heat pump, 2.8, and we are to determine the power of the heat pump draws when running. So when it runs, it need to be able to cater the heat loss at that particular rate, 22,000 kilojoule per hour. Okay. Again, let's describe the situation. In this case, then we have our house, and the house is losing heat. Okay, so Q out there in terms of loss. So Q loss is dot is 22,000 kilojoule per hour. And of course, we have heat pump to supply the heat that has to cover for the loss. Okay, that will be the QH dot. And of course, the heat is being supplied from outside, which is the cold surrounding. Okay, which is QL dot in this case. All right, and of course, in order for this to run, okay, to be possible, we require work net in dot. And you are also given the COP. In this case, this is heat pump, which is equals to, it is 2.8. Okay, so let's solve this problem. Remember the keyword, it runs, the pump only run 1/3 of a time. So let's say that if you are talking about 1 hour, only 1/3 of 1 hour is when the pump is running. So the other 2/3 of the time, then it is being turned off. So that 1/3 of the time should be able to cater for this 22,000 kilojoule per hour loss. Okay. So if we consider that, then what we are saying is that we need to supply the amount of energy that would to cater the amount of loss that we have there. Okay, so you need to be able to cater 3 times the load because it is 1/3. So what we have is QH dot should be basically 3 times the 22,000 kilojoules per hour rate. Okay, 1/3 of it to cater for the whole. Okay, and that is amounting to 66,000 kilojoule per hour load. Okay, our COP for heat pump is given as 2.8, and you know the relationship of COP is nothing but for heat pump is our interest is supplying the heat to the room, okay, and divided by the amount of work requires, okay, work dot. And if we rearrange this, since we know COP, we know also QH dot, we can find the amount of heat work requires. So rearrange that, work net in dot should be equals to QH dot divided by COP of heat pump. So in this case, then the amount of heat to be able, the heat pump should be able to cater is 66,000 kilojoule per hour. Okay, let's convert this to kilowatt. So in this case, then we know that hour to second is 3600. Okay, and of course, we know that 1 kilowatt is equals to 1 kilojoule per second. So that would be the conversion. COP, we know we are given as 2.8. So if you solve this, then you have the answer to become 6.55 kilowatt, meaning that the heat pump requires work of 6.55 kilowatt so that the pump will run 1/3 of a time to cater for the total loss, okay, during the situation there. Okay, I think that should be the first part. We will continue with the second part after this then. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.